It's Paul here with a graphical explanation of why Lagrange multipliers work. So what we're trying to do is find a constrained critical point in R2. That is, we're trying to maximize or minimize one function, little f, subject to the constraint that a second function, capital F, has a specified value. As the constraint function, I'm going to use something that's popular in economics called a Cobb-Douglas function. It's x to the 0.7 times y to the 0.3, and what makes it Cobb-Douglas is that the two exponents, 0.7 and 0.3, sum to 1. We will need a version of this function that takes a single vector argument. I make that as usual by replacing x by v sub 1, y by v sub 2. And now let's plot some contour lines for this function. There they are. And the problem I'm going to solve is finding what point on the contour line for 0.8 is closest to the origin. So what we want to do is minimize the distance to the origin. But a standard trick when you're solving problems with Lagrange multipliers is look for a function that's easier to work with that is a monotone function of your original function. So instead of trying to minimize the distance to the origin, I'll minimize the square of the distance to the origin, which is just as good. Now, there is in fact a clever way to solve this sort of problem graphically in 2 dimensions. We look at contour lines of the function little f that we're trying to minimize, and those of course are just going to turn out to be circles. So there are those contour lines plotted in red. And one way to think of this is you start a circle near the origin, grow it, grow it, grow it. As soon as it touches the 0.8 contour line, you have solved the problem. Looking at the diagram, you can see that the contour lines 1 and 1.5 lie on either side of the 0.8 contour line, and some contour line around 1.1 to 1.3 might actually touch that contour line at 0.8. Let's try it. Well, I've plotted 5 of those, and the one in the middle looks pretty good, but we can do better by zooming in and redrawing first our contour lines for the constraint function, then our contour lines for the function that we're trying to minimize, and the 5 contour lines that came closest to the solution. And it looks to me as though the contour line for 1.18 is the winner. Let's draw again with just that line. And now it looks as though we've solved our problem. But you see, numerically, we have a really nasty situation. The red contour line and the black contour line are very nearly tangent, but determining the exact point of tangency is extremely difficult because what we're trying to do is find the intersection of 2 lines that are nearly parallel. So let's read an approximate solution off the graph and then see if we can find a better way of solving the problem by looking for the intersection of lines that are nearly perpendicular instead of nearly parallel. So the best I could do is say x0 is 0.9, y0 is 0.61, and if I plot that, plausibly those 2 curves are tangent at that point. At least we found an approximate solution. Now, if the 2 contour lines are tangent to one another, they also have the same tangent space. And we know how to get the tangent space. It's the kernel of the Jacobian matrix. If you have 2 different Jacobian matrices that are proportional to one another, they will have exactly the same kernel, exactly the same tangent space. So we can't insist that the Jacobian matrices for the constraint capital F and the function little f that we're trying to minimize are equal, but we can say they have to be proportional in order to have the same tangent space. I've worked these out using techniques of ordinary calculus to get the Jacobians d capital F and d little f. I've evaluated them at my approximate solution, and if you look at them, you say, oh, the top one looks roughly 3 times as big as the bottom one. If I scale the second one so that the first components are equal, I find the second components are not quite equal. These are close to proportional, but they're not exactly proportional. If we find the exact solution, then they will be exactly proportional. So, let's set out to find a place where those two Jacobian matrices are proportional. This is the technique known as Lagrange multipliers, and the proportionality constant is the so-called Lagrange multiplier. If I go back and work algebraically with those formulas for d capital F and d little f, I can do a bit of algebra and discover that the solution is y equals the square root of 3/7 times x. In the real world, this algebra frequently does not work, but in Lagrange multiplier problems that are cooked up for introductory multivariable calculus courses, instructors work very hard to rig the problem so that you can actually do the algebra. And I'm afraid students get caught up in doing this algebra and entirely overlook the important part of solving the problem. So let's plot that line. Hey, that's pretty good. That line is perpendicular to both those curves, and finding the intersection of that black straight line with the contour line is going to be very easy. In fact, we can do it algebraically. Since we have y as a function of x, we can use that fact to eliminate y from the constraint equation. We can get a value for the constraint that depends only on x. The minus 0.8 reflects the fact that we want the constraint function to equal 0.8. So when we subtract off 0.8, we want something that's equal to 0. And if I plot that, well, the r function is called curve, but over this region, it's very hard to tell the difference between that curve and a straight line, isn't it? Here is our solution. We came fairly close. The value of the constraint came out to be too small by minus 0.0007, but we know how to deal with this. We just use one step of Newton's method to get an x1, and having found x1, we can find the corresponding y1 by using our constraint. There it is. Now let's see how we've done. df is the Jacobian matrix for the constraint function. d little f is the Jacobian matrix for the square of the distance from the origin. These two vectors look proportional. The simplest check is bind them together into a 2 by 2 matrix, take its determinant, which is 10 to the minus 13th. Those vectors really are proportional. And the coefficient in the equation d little f equals L times d capital F is the so-called Lagrange multiplier. When you're able to work conveniently with Greek letters, you will call that lambda. I've used capital L as a poor ASCII substitute for that. I can calculate that by taking the ratio of the first components or by taking the ratio of the second components. I get exactly the same ratio in both cases. Now think about it. If we form the function little f minus the Lagrange multiplier times capital F, then that has a Jacobian matrix that's exactly 0 at our solution. It has an unconstrained extremum. So let's make that function, and let's plot it. You look at those contour lines and you say, I know what's going on. In the middle of that ellipse, we've got a minimum. And there it is. So we've solved the problem. Now let's go back and display the solution we have found. The value of the constraint is obtained by plugging x1 and y1 into our constraint function. Comes out to be 0.8. The square of the distance from the origin is obtained by plugging our solution into little f. The distance from the origin is the square root of 1.178. And we can plot just the relevant contour lines. There's the contour line for our constraint. There's the contour line for the circle coming out from the origin. There's our solution, and you can see that at the solution, the two contour lines are tangent, and they have a common tangent space. All we have to do is find a basis vector for that tangent space, which is in the kernel of either d capital F or d little f, same kernel because they're proportional. By taking the ratio of components, I can find the slope of that line, and I can plot on my graph the common tangent line in blue, and there you have the general setup that occurs when you use Lagrange multipliers.